Okay, folks, let's kind of leave our discussion of enzyme mechanisms by talking big picture here. We have already seen a few examples of electrostatic stabilization. This is incredibly important for how enzymes work. How have we seen this in particular? Well, in the serine protease mechanism, for example, we had a transition state, that tetrahedral intermediate, with a negatively charged oxygen. So the mechanism was stabilized by some R groups that were performing hydrogen bonding or ion dipole interactions with that negative charged. We also just saw charge stabilization in the carbonic anhydrase mechanism with the zinc ion. How else do enzymes behave as catalysts? Well, they exert proximity effects. What do I mean by that? They bring the substrates close to the catalyst so that the reaction can happen. Let's imagine, right, some reaction happening free in solution like you do in a Gen Chem lab or an organic chemistry lab. What's happening is the molecules that you want to react are just like moving around in the beaker or the round bottom flask, right? And the reaction can't happen unless they literally and physically bump into one another. What an enzyme does in its active site is it kind of traps the substrate next to the catalyst. So for example, if we had some catalyst that needed to react with our substrate, if they were like covalently linked quickly to the enzyme, they couldn't really move around too much and get away from each other. They'd be stuck close to each other. And if they're close to each other, they're more likely to bump into each other and perform that reaction. But this really only affects the rate by about 5 times, which isn't a lot. So what else does the active site do? Well, it orients the substrates so that they are going to react well, right? When things bump together, they don't just automatically react. We need the bumping together to happen in a way where the orbitals are correctly aligned to form that new bond. As an example, probably one of the more simple examples we can think about is a reaction you learned way back in Organic Chemistry 1, the SN2 reaction. Pictured on the bottom right of the screen is an SN2 reaction. In this reaction, you see our nucleophile performing a nucleophilic attack, and its alignment is with this orbital it's about to bump into. You see how these orbitals are aligned with each other, right? If that nucleophile instead had been coming in from the side, it would not have been in alignment with any orbital to form a bond, so no reaction could happen. So what enzymes do, not only are they bringing these substrates close together, they are aligning them so that when they bump, the reaction can happen. And this increases rates by 100 times. Most importantly, though, these substrates are being bound within the active site, right? We have the catalytic site, but we also have the binding site. The binding site is critical for limiting translational and rotational movement. So what do I mean by this? We mean that the substrate is not moving back and forth, kind of bouncing around, and it's also not rolling around, right? So the active site, the binding site in particular, is kind of holding on to the substrates and not allowing them to move or roll in any way. This can increase the rate by 10 to the 7, which is a huge deal. Now you might be thinking to yourself, oh no, but if we hold on to things and they can't move, then the entropy is decreased. But that is all right. Overall, this is still favorable. We'll still have a favorable Gibbs free energy because of all of those favorable interactions happening in the binding site, right? Think some type of electrostatic interaction, maybe some hydrogen bonding, or if it's nonpolar, maybe just a bunch of London dispersion forces. One last thing that I do want to mention, but won't be a focus of the class, folks, is that in addition to electrostatic interactions that help to stabilize charge, in addition to proximity effects, orientation effects, and limiting movement, enzymes can constrain the substrate in such a way, and it was kind of alluded to on this slide, enzymes can bind their substrate in such a way to kind of mimic the transition state. What do I mean by this? Well, for example, folks, in our serine protease mechanism, this is a kind of a clear example. We have a substrate that is this carbonyl arrangement, right? Since we have some sp2 hybridized carbons, this is trigonal planar. But the transition state has the carbon making 4 bonds. And if I were drawing this, appropriately, I'd use the type of geometry that you learned in organic chemistry to show you that we are no longer trigonal planar, we are tetrahedral, right? So an enzyme could bind to its substrate if it were trigonal planar and kind of bend those bonds so that they looked more tetrahedral in terms of their bond angles. Now, this would help push the reaction forward because the substrate already literally physically is looking more like the transition state. So this would lower the activation energy and push that reaction along. And it's hypothesized that some enzymes actually bind the transition state more tightly than either substrate or product because they make maybe more interactions, more non-covalent interactions in that transition state. That is all for today, folks. We learned really one new mechanism, but we talked a bit more about covalent catalysis as well. We learned some additional considerations other than just electrostatic stabilization of substrates that are going to help contribute to the active site. These are all things we want to think of, especially as we consider our homework where we are building our very own enzyme active site. And with that, I leave you with this cat meme.